Hello and welcome to our seminar today, Fast Sequential Peptide Synthesis, Addressing the Synthesis and Purification Bottlenecks. I am your moderator, Michelle. Our presenter today is Michael Carney, Product Manager for CEM's Life Sciences Division. Michael is a key member of our R&D team and has been instrumental in developing new products and using existing products to develop new chemical methodologies. There will be a Q&A session at the end of the seminar, so please feel free to send in your questions via the question panel at any time during the presentation. So let's get started. Thank you for joining us today, Michael.
Thanks a lot, Michelle, and thank you for the kind introduction. So as Michelle said, today we're going to be talking about some of the problems that you encounter, the synthetic steps of peptide synthesis, and then how that kind of relays into issues that you might see in the purification side of the whole process. So we'll get started right away with what's done with the traditional, how you perform a traditional 20-mer peptide synthesis. So typically you'll see here on this portion of the screen, the synthesis time takes a good long portion of the total time. So between synthesis and cleavage, we have almost 24 hours, a full 24 hours of labor that's involved. Then onto analysis and purification, lyophilization. That rounds out, following 9 hours to make a 20-mer peptide in the traditional sense using room temperature synthesis and conventional methods. Since about 2004, we've tried to look at this portion of it, the synthesis and cleavage side, to make sure that we can address some of the problems there with slow reaction times and lengthy protocols in general. So to do that, since 2004, we've introduced microwave radiation for heating all coupling and deprotection steps of a peptide synthesis process, as well as the actual cleavage step as well. With the advent of UPLC technology from chromatography companies, we've really accelerated the analysis side as well. So even though we have managed to accelerate the beginning portion, the synthesis and cleavage portion peptide synthesis process, there's still something that we like to call the synthesis bottleneck. So this has come up more recently as a result of the high demand for peptide drugs in the market. Now, they've become very attractive candidates. This high demand is kind of converse to what we see as kind of a drop in the small molecule demand. And as this demand in the market's getting more and more enlarging, we do have some issues with the initial short-chain peptides that many people were interested in. You can see more and more people interested in longer-chain complex peptides that require more synthetic steps, and so you need to ensure you get a more complete reaction at each step in the process. Otherwise, you result in a low purity or lower yield. And there are also difficult non-natural modifications which are incorporated into these peptides, further complicating the synthetic challenges. So what we did to address this synthesis bottleneck, this need for a large number of peptides and a large number of difficult and diverse peptides, is last year CEM introduced the Liberty Blue next generation microwave peptide synthesizer. Kind of some of the hallmarks of this system, we released it last year. We did a webinar on it last year, so I'm not going to go too in depth on it, but I wanted to bring everybody up to speed on kind of some of the current technology. The hallmark is a 4-minute cycle time, so we've drastically improved the rate of reaction and the chemistry involved with peptide synthesis. This means that you can make a 30-mer in only about 2 hours' time, so you can really come in, program it, get a cup of coffee, and by lunch you could have a cleaved and analyzed material. In addition, we've optimized the number of the washing steps to reduce solvent consumption greatly, so 90% solvent reduction over previous systems. In addition, because you get to run the reaction very quickly at a high temperature, this can result in improved purity for your peptides. So it makes it very easy to then say, all right, I can quickly queue up a number of peptides and synthesize 24 peptides in something like 40 hours. And this is something that we see, I'll touch on a little bit later. What we like to say is that this fast sequential process fits very well into lab workflows, and is something that can even replace parallel processes. So I'll get a little bit into how we actually, made the Liberty Blue so efficient. And so it was a combination of both hardware optimization as well as chemistry optimization. What we had was an idea for an improvement in the chemistry and then designed a system around it. On the chemistry side, what we did was we managed to reduce the total chemistry time to only about 3 minutes. This is 75% of the overall cycle time. I'll get a little bit into the details of how we did that in a few slides. On the hardware side, what we managed to do was reduce the liquid handling, so all washing, all reagent prep, and queuing up reagents in manifolds to only 1 minute. So this is 25% of the overall cycle time. What we like to call the Liberty Blue, and this process is a high-efficiency solid-phase peptide synthesis, or HE-SPPS, as you can see on the top. And we call this a game-changing technology, really, because it's orders of magnitude faster than the existing technologies. So 10 times faster than our first-generation microwave Liberty peptide synthesizers, and 30 times faster than conventional syntheses. What we've done here, as we like to say, is eliminate the synthesis bottleneck. We can now accommodate the need for a large number of peptides and a large number of diverse peptides in a very short amount of time. This bar graph really drives it home, I think, when you look at the overall time required for a kind of conventional process and the fact that now, using Liberty Blue and the high-efficiency process, we've really reduced the overall synthesis time, including cleavage, to about the same amount of time required for peptide purification. So on the chemistry front for our high-efficiency process, I'll break down the actual cycle a little bit more. We've decreased the reaction time for both coupling and also deprotection steps. So what we do here is only a 1-minute coupling, actually about 65 seconds total. Rather deprotection step. And the coupling step's about 125, 130 seconds total for about 1 minute and 2 minutes respectively. And the way that we can do this is because we run our reactions at a increased temperature. We run both deprotections and couplings at 90 degrees Celsius using a DIC-oxima activation strategy. So we've also managed to maximize the use of microwave energy. In this case, we need a microwave to really allow precise and accurate control of our temperature. As you could imagine, when you're up at high temperatures, it's very, very important to be very, very defined with your control. Any kind of variation from that, if you use an inaccurate temperature monitoring method, can result in poor peptide quality. In addition, we've seen that running at these higher temperatures and looking more and more closely at the peptide synthesis process, we've been able to eliminate a lot of the washing involved. So first of all, we've decreased the number of washes. We've eliminated washing after coupling, because what we can use is the concentrated deprotection solution to just quench all activated ester and eliminate the need for extra steps for washing. In addition, we've been able to reduce the volume of washing and also number of washings after deprotect by running reactions up at a higher temperature at 90 degrees Celsius. What we've seen is that now we have better mass transfer between our resin and our solution. So we can more quickly extract contaminants from solution, or rather from the resin, and elute them outside the reaction vessel. What we've also done is remove the need for background washing. So we have incorporated the actual washing of the manifolds into final washing steps, so we ensure that everything is clean and extremely quickly. On the hardware side, we've eliminated a number of the restriction points involved in most systems. This allows for a faster reagent flow as well as faster washing, in addition to isolating the bubbling and reagent handling lines. This is a very, very important improvement, which allows us to do a number of operations in the background while we're actually, running other operations in the foreground in the reaction vessel. What this has done is improved both our draining procedures and also nitrogen bubbling for agitation. Finally, what we've done is use a patented technology called FlexAdd technology to develop a pressure-based reagent addition strategy. So this doesn't use any liquid sensors. There's no need for those optical sensors to confirm reagent volumes. And so this allows for pretty much unlimited variability in a range of different reagents or solvents that you're adding. So you can dial in pretty much any number that you want for a volume to add, and the system will add it very accurately and consistently. So I mentioned before that we take advantage of microwave control to have that precise and accurate control of temperature when we're running this microwave chemistry. So microwave allows, and the sequential process allows for complete control of microwave energy at each step of your reaction. This is extremely important, when it comes to unique amino acids. So a number of known side reactions, in this case, histidine requires a 50-degree coupling to prevent racemization. Maybe you have some special derivatives, phosphoamino acids or glycoamino acids. They might require room temperature deprotections. And so
Michael, could you
Yep.
hold on just a second? I'm sorry, but apparently some people are having difficulty hearing you.
Okay.
If you are having trouble hearing Michael right now, could you please click on the raise your hand button on your control board?
Does it look like it's a large proportion of people?
No, not an awful lot. So if you're having trouble hearing, maybe check your speakers, because we don't seem to have too many people with that difficulty. And if you continue to have difficulty, I would suggest please phoning in for the seminar so that you can hear better instead of using the speakers on your computer. You might also try if you have a cell phone or an iPad, something nearby your laptop. Sometimes that can interfere with the signal, so I would suggest moving it away from your computer. And please keep in mind that the webinar is being recorded, so it will be available for download later, and you will receive a link for that. Okay, I'm sorry, Michael, go ahead.
All right, thanks a lot, Michelle. It's all right. We want to make sure everybody can get the full effect for the webinar, but as long as you can hear it recorded, that'll be just as good. So as I was mentioning, the sequential process allows for very exact control of microwave energy at each step, so ensure that you're not heating too much when you don't need to, but at the same time when you're heating enough when you need to. So some high energy processes, if you're trying to couple very sterically hindered residues, whether they be dimethyl or N-methylated peptides or rather amino acids, these typically require a higher temperature, a little bit more kinetic energy to get that coupling to go. So again, the sequential process allows for this tight control of reaction parameters at each step for each coupling and each deprotection of your peptide. And what this translates into, this tight control, is really excellent results overall. So this is a comparison of a series of 6 peptides that we synthesized. We have some short chain in there, some that suffer from aggregation, and then obviously some of these really long chain difficult sequences that we synthesized using conventional methods as well as compared to our first generation Liberty methods. So you get a big bump just by using microwave energy and heating up the reaction to drive it forward. But then compared the first generation Liberty to the Liberty Blue methods, really what we see is either comparable or superior results in all cases. And Liberty Blue takes advantage of these faster methods, so it's done faster than the first generation Liberty, as well as these more solvent-efficient methods. So you're going to be consuming less solvent, producing less waste, and it's going to be an overall greener process. And this summary slide really, I think, kind of drives home that speed and that solvent savings. So what we have here, I've just moved the purities from that previous slide over here. But we see the total synthesis time in this case. So we have 10 mers synthesized in less than an hour. Here we have 20 mers synthesized in about 2 hours, a little bit less. And then here, longer chain. So we have a long chain, over a 40 mer beta amyloid. This is synthesized in less than 4 hours time. And the big thing is also it produces only about 1 liter of waste. So now you have, drastically less waste that you're producing, in addition to having it done much, much faster. If you're looking for more details on this method and some of the chemistry performed here and some of the details, I'll direct you to our organic letters paper published earlier this year, as referenced down here. And again, what this shows is really the fact that you can actually come in, as I'd said before, start a sequence and have something, a cleaved 40 mer in this case, by just after lunchtime. So it really lets you improve your optimization for different reactions, and especially when it comes to difficult long chain peptide chemistry. What's nice is the short chains, you have them done in less than an hour. You pretty much have barely the time to get back to your desk, check an email, and get back to the machine, and the sequence is already done. And just to show, some of the quality chromatograms we get, this is the kind of chromatogram that we want to see, and we're extremely happy with, when we get it off of our Liberty Blue system. So this example is beta amyloid here. Have the synthesis conditions using low-loading PalPeg resin, and again, kind of reiterating that quick synthesis time, that low chemical waste production, and the high purity we produce from this. A nice single peak coming up here with very, very little byproducts on the side. So revisiting our initial diagram, what we've done here is address this initial portion. So here, using our high efficiency process, we really trimmed the synthesis of a 20-mer down to about an hour and a half, with cleavage rounding out, the other half hour, for a 2-hour process overall to make a 20-mer. Whereas previously, using traditional methods, it was almost a day. But what we've done is now, so since we can synthesize peptides so quickly, we've kind of pushed a little bit of the weight onto the analysis and purification side. So here, what we do is we see something that we like to call now the purification bottleneck. And this comes as a result of the need and the ability to synthesize this, many, many peptides. So some of it comes from that synthesis bottleneck. You have a desire for a lot of material, you need to make it. We've accommodated that with Liberty Blue. And so now, what you have to do is try and purify all of it. In the case of this purification issue that we've seen, typically parallel synthesis formats are the industry standard. This is something, kind of a block synthesis system, which will make 24, 48, or any number of multiple peptides parallel, so all at the same time. The problem that you end up having is, once the synthesis process finishes, what you end up with is then 12, 24, however many peptides that now need to be analyzed and purified. So all you're doing is now making an issue for your purification equipment. You're overloading it, where instead what you're doing is running maybe a 3 or 4 or 5-day synthesis, and then you're spending the entire next week worrying about purification and analysis. And this is something that really disrupts your laboratory workflow. Instead of being able to make educated decisions about how you want to optimize a reaction, kind of on the fly, you're stuck with waiting until you have the entire process done before you can decide and plan out what your next steps are going to be. This is something that's also kind of exacerbated this purification bottleneck by the long purification times typically required. And this is as a result of, lower purity peptides, so you'll need to run more complex methods. You'll need to run multiple, chromatography runs to be able to isolate material. And as you're running more runs, you're reducing your amount of isolated material, so then you might need to go back, resynthesize, so you're wasting more reagents, more solvent to make more material, just so that you can end up with X amount of isolated product. And so what we've done to try and address this purification bottleneck is take that idea of a fast sequential synthesis and adapt it to an automated format for our Liberty Blue system. And this is what we like to call the Liberty Blue HT, or high throughput system. So this consists of our Liberty Blue module, seen here, as well as an automated resin loader. So here you have either a 12 position, or you can add on another 12 position for a total of 24 different resins and different peptides that you can run. And it runs entirely automated, so totally hands-free. What you would do is go ahead, you can prep your first reaction, put it on the system, and start it up. And it'll get started right away, synthesizing, doing your deprotection, coupling, washing, everything. And then go ahead and prep your other reactions afterward, so you can actually get started right away. And then by the time you finish prepping all your reactions, who knows, if you're running a short chain peptide, you might be done already. It might take you 45 minutes, to prep those 24, and then you can start cleaving and analyzing. And so this is something, as I'd said before, is really where we see that a fast sequential synthesis is something that can replace parallel synthesis strategies. So the advantage is that you get single peptides very quickly. As I'd mentioned, if you're running a short chain or moderate chain peptide, you're done in an hour or two. It also eliminates this purification bottleneck. So instead of having this glut of crude peptide that you need to worry about now purifying and analyzing, the system will finish a peptide. Once it finishes, it'll transfer back to its corresponding resin position. You can then take that position off of the system, cleave, analyze, get results, so that, say you have a derivative of that a peptide that's being run at a later position, say number 23 or 24, you can go ahead and make educated decisions based on the data that you have from your first run to modify for that, instead of trying to run everything all at once and generate a table from just one go. You can generate a more educated table on the fly. In addition, you also have a much less complex instrumentation in this case, so instead of having to worry about any kind of robotics or complicated syringe pumps, what you have is a simple rotary valve system which will transfer out, again, using pressure, and then transfer back to the resin positions. In addition, as I had said before about microwave energy, this sequential process allows for precise control of each step. You can run one position, very labile compounds, as I said, glycopeptides or phosphopeptides, and then run all naturals in the next one, then some unnaturals with very difficult couplings, in the next sequence, and again, have that precise control over each step so that you end up with a higher purity synthesis at the end. What this really does is this eliminates some of the throughput advantages that you can see in obsolete methods, and really, in parallel methods, and really obsoletes these approaches entirely. So what we decided to do to kind of validate this was take a look at a high throughput study for our HT12. Our experiment was pretty simple. We just wanted to synthesize 12 different derivatives of ACP. On the HT12, what we did was vary the final amino acid to be added on so that we would then analyze by UPLC-MS with the goal of examining our transfer efficiency, making sure that this was a reasonable time frame that we were requiring for going through the process. Look at the total synthesis time to ensure that this wasn't impacting the dramatic efficiency in Liberty Blue. And most importantly, since you were using the same reaction vessel for multiple reactions, or rather for multiple different peptides and resins, we wanted to ensure that there was no cross-contamination as you were removing resin, peptide on resin from the reaction vessel and putting it back in its position. So this next table shows the sequences that we decided to run. Here we have, ACP and then our various ACP derivatives here, all of them with unique molecular weights to make it easier to identify contamination in our UPLC traces. And as we expected, thankfully, we saw that UPLC crude purity was extremely high in all cases. We saw some pyroglutamate formation here and then some methionine oxidation in some of the cases, but overall, extremely high purity. And the most important part is that none of the sequences, none of the chromatography traces, rather, showed any kind of byproduct or any kind of cross-contamination between the various sequences that we ran. So the end result that we had was, for running all of these 12 peptides with no cross-contamination or anything, high purities, we had a total synthesis time in this case of just about 13.5 hours. And really the big points for this, since they were pretty straightforward sequences, is that we had only about over a liter of DMF used for our wash solvent, producing only 2 liters of total chemical waste in this case. So we were able to synthesize 12 peptides, making only 2 liters of waste, which is almost unheard of. And so what this makes us do, as I said, is kind of rethink the parallel format and the parallel idea of how you're going to process, peptide synthesis, peptide samples rather. So instead of using the kind of case study of saying, we're going to synthesize 24 20-mer peptides and compare it, hypothetically on Liberty Blue or on other typical parallel synthesizer. In this case, we're using a 4-minute cycle time for our blue. This is the average cycle time with a 7-minute transfer time between different peptides, different resins that you're running, for an overall synthesis time of only 35 hours. So here, what we're able to do is not only synthesize all 24 20-mers in less time than the parallel synthesizer, but the big point is, again, you're not stuck with that glut of crude peptides. When the HT finishes one resin, one peptide, you can take that off, cleave it, and analyze it. So at the end of that 35 hours, you don't need to perform analysis at that point. You've already analyzed all of your material. Here, after those 40 hours, you still need to analyze all of your samples and plug through that long, arduous journey, for your poor HPLC or UPLC running for, hours on end. In addition, I'll drive home that point again of that complete control. So we end up with higher purity peptide, and the end result is that you're also saving a lot of money from using a lot less solvent. So I had mentioned the Liberty Blue is going to save you a lot of solvent up front. In this case, we're showing a hypothetical example, peptide house that's producing 15 mer peptides, so shorter chain peptides, about 20 a day for a total of about 5,000 in a year. Using these numbers, you can see, you're consuming a lot of solvent, over 8,000 liters of solvent a year, using a standard, kind of parallel system or a normal conventional process for peptide synthesis. The Liberty Blue cuts that solvent consumption down a lot. Here we're down to just, a hair over 1,300 liters for savings of almost 7,000 liters a year. And as you could imagine, this translates into drastic, cost savings when it comes to purchasing. But also when it comes to disposal, again, using less solvent is going to result in producing less waste. And besides that, on the front end, besides on the synthesis end, you also do save a lot when it comes to your purification costs. Crude purities are typically a lot higher on the Liberty Blue than you'll see with conventional processes. I had shown this in some previous slides. With many of your crude purities being over 70%. So depending on your application, you might only need one synthetic, or rather one purification pass through to a chromatographic instrument, or you might not need any at all. Really, your purification is significantly easier. So in addition to consuming less synthesis solvent and producing less synthesis waste, you're also consuming and producing less purification solvent and waste. So I'll summarize very briefly here, looking at the fact that really to address the synthesis bottleneck, we've come up with a system that can make any peptide fast, really. A combination of our high efficiency process, so running at higher temperatures, using a specific activation and deprotection strategy, and the Liberty Blue, so that advanced fluidics handling of the Liberty Blue, it really fits perfectly together to make your results shine and accommodate any kind of synthesis need, whether it be short chain, high production, or long chain, very complex sequences. On the purification side, by coupling, the speed of the Liberty Blue with an automated process, so an automated, fast sequential process, it reduces some of your purification woes that you see with parallel formats where you're stuck, as I'd said, sitting in front of UPLC or an HPLC for hours on end waiting to get results. So this HT12 with a fast sequential process really replaces what you can do in a parallel format. And as I said, the high crude purities that you get from the Liberty Blue system reduces the overall purification workload for your systems. You don't need to worry about, as I said, multiple passes through a column to be able to get purified product. And so we see that at CEM as the Liberty Blue HD kind of being this next generation of peptide synthesis. So looking at the problems that we're encountering today in a new light and addressing them in a new and revolutionary way. So I'd like to thank everybody very much for your time. We wanted to keep this kind of short today, so we allowed for some Q&A time. And if you want more information, because this was by no means an exhaustive webinar, you can go to our website, cem.com. If you're in the U.S. or Canada, our territory sales manager, Greg LeBlanc, said you can reach out to him directly. You can email him here at greg.leblanc@cem.com. Outside of North America, anybody from any other parts of the world, you can email info@cem.com for more info, or anybody can call in if you want. Talk to myself, talk to one of our application specialists or product specialists to get a little bit more information on the systems and see if you have any questions, how we can fit your needs and solve your problems that you have in your synthetic labs. So I'd like to thank everybody again, and thank you, Michelle, for hosting us today.
Oh, thank you, Michael. It was very informative. And we are getting a few questions in here, so please go ahead and type your questions into the question panel if there's anything you'd like to know. First off, you mentioned a temperature condition of 90 degrees. Has that been validated with something like Bach protected side chains, or should those be avoided to prevent thermal deprotection?
No, so that has been validated with Bach protected side chains. The 90 degrees, so we run the 90 degrees you saw for 2-minute coupling, 1-minute deprotection, and we run that on a number of sequences. So again, this is strictly FMOC chemistry that we're running, but as far as Bach's protected side chains, that's just fine. We'll see problems I'd mentioned with histidine. You want to run that at lower temperature. I'd mentioned the amino acids, glycoamino acids. They can be a problem sometimes, but we haven't seen any thermal deprotection of any other, any side chain protecting groups at all in our studies.
Oh, good. Another question here. For people still doing manual synthesis, no automation, what tips can you give them to take back to the lab today? And can they also heat the reaction to cut washings?
Yep. Yeah, so this is something that the chemistry that we kind of disclosed here, and we disclosed, as I said, in that organic letters paper, it's not exclusive to the Liberty Blue. What we've done is we've crafted, an instrument around these chemistry improvements to take even more advantage of the time savings that we see. So really optimize it to the extreme. When it comes to, performing conventional or manual syntheses rather, you can still heat up your reactions. Microwave just offers an excellent format for rapid heating and also precise heating, because temperature control is important when you're performing these. So when it comes to manual synthesis, it might be a little bit difficult to maintain a higher temperature. We have seen drastic differences between as little as 75 degrees and the 90-degree methods in terms of the efficiency of washing. So for us, we've really the reproducibility that we get from the automation. That's what lets us, be very, very precise with the amount of washing that we're doing and the volume of washing. It can be a little bit difficult to do that in the manual format, but as I said, I'd really reference you, or rather push you towards the organic letters paper to see, as I said, some of the chemistry improvements, because there was additional material that I didn't really get to cover today.
Okay, good. Do you have strict requirements for what grade of DMF that you use?
We do have requirements for the DMF that we use. We recommend spectrophotometric grade or better, so typically higher than ACS reagent grade. This is, for a number of reasons. One thing we've actually seen is that lower purity DMF, some of the byproducts from the industrial process can actually kill activated esters at higher temperatures. So sometimes customers may have some issues with synthesis. They say, there might be a problem, with our chemistry, but really what it is the reagents. The reagents will actually end up quenching, your coupling, your activated ester. So you'll end up seeing deletions in sequences. So yes, there is a purity requirement. As I had said, it's higher than ACS grade, typically spectrophotometric grade.
Okay. Along the same lines, are you restricted in the chemicals that you use in the couplings?
No, not entirely. So in the case of all the stuff that I presented here, this kind of high efficiency stuff, we use DIC Oxima as our activation strategy, and we prefer that acidic strategy for a number of reasons. You can use HBTU, HCTU, HATU, so any of the uranium activators with DIEA, or you can use HOBT still. HOBT is kind of a easy trade-in for Oxima. In many cases, people will have HOBT but won't have Oxima in their lab. The acidic strategy we prefer because you don't get any racemization from histidine at higher temperatures using the acidic strategy. That racemization is due in part to the DIEA that you end up using with uranium activation strategies. So by avoiding that, by keeping your coupling solution slightly acidic, you don't racemize any cysteine. It also reduces, we've seen recently, that it reduces gamma-lactam formation significantly. So again, this is, some of the side reactions that are common with higher temperature synthesis. The the DIC Oxima or DIC HOBT activation strategy really circumvents a lot of those issues. So you can use a wide variety of coupling reagents on the system. We just prefer, and we kind of push people towards DIC Oxima because it's seen to operate the best at the higher temperatures.
Okay. Again, along the same lines there, are there purity requirements for any other reagents? As TFA, DIPEA?
Yeah, we usually recommend, a very high purity. I don't know off the top of my head the ones that we recommend for reagents. We have seen some issues again with, low purity starting materials, so low purity amino acids or, kind of dirty TFA, used in cleavage. This is actually, kind of a case study that we've seen recently. Somebody was having, we were having some issues with cleavage in our lab, and we realized that we were using a slightly older, I don't remember exactly how old, TFA rather than fresh TFA, resulting in poor cleavage under our microwave conditions, and then as a result, we were seeing poor, peptide purity. We think it's something wrong with the sequence or something wrong with the system, but it's not. It's just our, our cleavage conditions. So we do have, requirements, for other reagents as well. If you're interested, you can, provide either email me or email info@cem.com, and we'll provide you with those exact parameters.
Okay, good. Will DIC Oxima work with first-generation Liberty synthesizers?
Yes, so we actually do have, I think we have an application note actually for adapting your Liberty or Liberty One to the DIC oximer chemistry and the high temperature chemistry. So you can run up at 90 degrees Celsius, so you get that drastic rate enhancement during the actual coupling and deprotection steps. But because the fluidics are fundamentally different, you don't get as much of a time savings. So the way that we have the washing and bubbling handling in the Liberty and the Liberty One, you can't do as many background operations. So it's a sequential process, but you can still accelerate your actual coupling and deprotection steps. I would recommend emailing info@cem.com again. We can provide you with that application note if you're interested, so that you can get started with the chemistry right away.
Okay. For PEG-based resins like Chematrix resin, can those be used in a microwave synthesizer?
Yes, absolutely. So we actually have built-in methods for Liberty Blue for low swelling, well, standard swelling resins, and high swelling, like Chematrix or Palpeg resins. Where you're going to need a little bit more washing solvent when you're washing. As you could imagine, the volume is going to be a little bit larger for a synthesis scale, so you want to ensure it's completely covered. But that's any PEG or Chematrix resin is entirely amenable to microwave synthesis.
Okay. We have someone here who is currently using a CM Discover microwave reactor, only manually. Can they heat it to 90 degrees during peptide synthesis?
So yes, you can. The one caveat I'd have for that is that you really, really need fiber optic temperature control when it comes to using these precise 90-degree methods. We use fiber optic on Liberty Blue exclusively because IR is not a reliable enough metric for some of these coupling reactions and deprotection reactions. So we actually have a semi-automated system. So if you already have a LabMate or a Benchmate or any Discover Discover product, as long as it's a legacy Discover product, so not a Discover SP, you can actually upgrade to a semi-automated system that we have, the Discover Bio, or you can upgrade right to Liberty Blue as well. It's pretty much you get the fluidics handling that would go with it. But again, if you're going to do it manually on a Discover, I would say you really want fiber optic to ensure you have accurate temperature measurement. Then for the 90-degree methods, you can still run 75-degree methods if you want. So it's like 75-degree methods with HBTU DIEA. That works pretty well. And those are kind of our legacy Liberty methods. So if you're familiar with those, yes, you can run those, just standard on a Discover.
Okay, good. The 30-minute cleavage step you showed in a few slides, how is that done?
So that's actually using our Accent microwave cleavage system. This is something that we use which runs your cleavage at 38 degrees Celsius. It takes only 30 minutes. And it's pretty much a microwave, so a Discover with an associated washing station. And it fits really well with the HT workflow. So pretty much with a Liberty Blue or an HT, as soon as you finish a peptide, you can run it on your Accent, cleave it in 30 minutes, and then analyze it immediately. So in the case of a 12, an HT12, say you walk in, in the morning, you have 12 completed peptides. You can actually, take 6 and start a room temperature cleavage, for 3 hours, and then take the other 6, run them on the Accent, and they'll actually all be done at the same time. So it can really accelerate, that cleavage part of your steps, part of your purification process.
Okay, good. And that basically brings us to the end of our program. Oh, one more. Can 2-chlorine TRT resin be used in microwave synthesis?
Yes, so you can use chloroturtle resins, no problem. Thank you, Michelle. That was excellent.
Sorry.
You can use chloroturtle resins. So as you could imagine, being acid labile, you typically want to run them at a lower temperature, and we actually do recommend it. So in the case of any chloroturtle resin, we do recommend actually running HBTU DIEA or HATU using a uranium or a more alkaline activation strategy, just to avoid any kind of a premature cleavage from of your peptide from the resin. So chloroturtle resins are just safe to use. We just run them at a lower temperature for a little bit longer time. But for any standard non-acid labile linker, you can go ahead and run your 90-degree DIC methods.
Okay, great, wonderful. Well, is there any special loading method for loading non-FMOC
Yep.
I am not doing well on this.
No, you're doing well.
Is there any special loading method for loading non-FMOG protected resins, i.e. NovaPeg or ChemMatrix? What is the preferred activator?
Doing an acid loading, we do have a method which we're actually in progress working out with microwave. So we don't have that in place yet, but we're working on that application right now. Just a simple, easy method to quantitatively, add on, your first amino acid to the resin.
Okay, great. Well, apparently we have reached the end of our questions today.
Okay.
Thanks, Michael.
I was going to say, if anybody has any questions, again, it's cm.com or info@CEM is going to be a great resource. That way we can kind of get it together and direct it to the right groups at CEM.
Thank you so much for your time today, and we really appreciate you explaining everything. Again, please contact us if you have any questions. We'd be happy to talk to you. And we really appreciate your time today. Thank you and have a wonderful day.